So now that we've gone over all of this, including resonance and formal charges, let's go ahead and look at a few examples for illustrative purposes. So just like in class, what I'm going to do is encourage you to pause the video and try to draw each of these on your own, and then I will walk you through how to determine the answer for the correct Lewis structure for each of these examples. So this first example is going to be to draw the Lewis structure of the compound with formula C2H5Cl. And for this, notice that most of the atoms here are carbon and hydrogen. When you attempt this problem, just know that you can apply those rules where carbon should normally form 4 bonds, hydrogen should form 1, and in this case, chlorine, like most halogens, will form just a single bond. So see if you can come up with what the right answer to that is. So go ahead and pause the video, and I'll come back in a second. Okay, so hopefully you've attempted this problem on your own. Let's go ahead and actually draw this. So the first step of drawing any Lewis structure, of course, is going to be to determine how many valence electrons we have. So step 1. And we have 2 carbons, so 2 times the number of valence electrons in a carbon atom, which is going to be 4, plus we have 5 hydrogens, so 5 times the number of valence electrons in a hydrogen atom, which is 1. And then to that, we're going to add the number of valence electrons from 1 chlorine atom, which, since it's a halogen, will be 7. So 2 times 4 is 8, 5 times 1 is 5, and 1 times 7 is 7. So altogether, this should give us, let's see, 8 and 5 is 13, plus 7 is 20 electrons. And specifically 20 valence electrons, but those are the only ones that we want to incorporate into our Lewis structure. Now, remember, carbon is pretty much always the best choice for a central atom, if it is in the molecule at all. And in fact, this formula might remind you of the example of ethane from a few slides ago, which was C2H6. And if you remember back to that molecule, we had a carbon-carbon single bond, and we had some hydrogens, 3 hydrogens attached to each molecule. Or I'm sorry, each carbon. So 3 hydrogens on that carbon, and if this was ethane, we'd have 3 hydrogens on the rightmost carbon too, but notice we only have 5 hydrogens and 1 chlorine here. So we're going to replace one of these carbon-hydrogen single bonds with a carbon-chlorine single bond. And so something like this is going to be the best structure for C2H5Cl. Now, putting this skeleton together is essentially what step 2 is. So if we count how many single bonds we have 1, 2, 3, 4, 5, 6, 7. So there aren't any lone pairs on this molecule yet, but we have 7 bonding pairs of electrons, which means that we've used up 14 of our 20 electrons that we started with. And so we have 6 remaining after that step. Now, step 3 is to assign those electrons to outside atoms to complete their octet. And let me go ahead and erase those dots just so they don't look like electrons. All right, there we go. Now, we have, as outside atoms, we have hydrogens and we have chlorine. Now, hydrogen shouldn't ever have any lone pairs on it. It should only have one single bond to something else, and that's it. Our chlorine, though, wants to have a complete octet, and it currently only has access to one single bond here. So this thing needs 6 more electrons, and as it turns out, that's exactly how many we have left to place in this molecule. So we can add 3 lone pairs to this to account for those 6 electrons. So that uses up all of the remaining electrons. And so we have this Lewis structure here. 3 lone pairs around our chlorine. And so since we're out of electrons, there is nothing to do at step 4. We can't assign any lone pairs to any carbons or anything. And then step 5 asks us to examine the central atom, or atoms, which would be the carbon atoms, and to determine if they have complete octets. So each of these carbons is surrounded by 4 bonding pairs of electrons. So in the case of the carbon on the left, that is 3 carbon-hydrogen bonds and 1 carbon-carbon bond. And in the case of the carbon on the right, that's going to be, again, this carbon-carbon bond, and then 2 carbon-hydrogen bonds and a carbon-chlorine bond. So each of those has access to exactly 8 valence electrons, and so we are basically, we've accounted correctly for all of the electrons that should be around those carbons. And so the structure you see here is the correct one for C2H5Cl. Now, a word of clarification on where this chlorine went. You might be looking at the structure and wondering, say if we compare this to ethane, let me go ahead and scroll back a few slides to that. You might be wondering, why did we replace this particular hydrogen in the structure with a chlorine? And the answer is it doesn't matter which of the hydrogens were you essentially replaced with a chlorine here, because they're all basically identical. So that might seem a little bit strange at this point, but just know, for instance, that what you see here would be exactly the same as, say, something like this, where you could have a chlorine on some other part of that same carbon, or indeed you could have a chlorine atom on the other carbon atom as well. So something like this. So any of those 6 hydrogens can equally be substituted with a chlorine, and you'll get the right answer. And whenever you're given a chemical formula like this in any of these examples that you have to try on your own, the answer you get will be unambiguous, so you won't end up with a situation where you need to pick one of several possible forms. So that's that example. Let's go ahead and look at this next one, BF3. This is boron trifluoride. Now, I want to go over this example for one sort of violation of the octet rule that we haven't really covered yet, which specifically involves boron, and I guess other elements in the same family, so like aluminum and gallium, but boron is really the main culprit here. So what we're going to do is we're just going to start drawing this like normal. Boron has 3 valence electrons, so there's just 1 boron, so we have 3 valence electrons from that. And then our fluorines each have 7 valence electrons, and there are 3 of those. So we need 3 times 7 for that. 3 times 7 is 21. Add 3 more to that, we get 24 electrons. So that's the number of electrons we have to place in this Lewis structure. So let's go ahead and move on to the next step. Now, fluorine shouldn't ever really be the central atom in any of these molecules we draw. It's so electronegative, and it only ever forms one single bond to anything else. So we're going to put boron in the middle of this molecule. And we'll attach the 3 fluorines to that. And so our 3 fluorines will be on the outside of this molecule. So we have 3 single bonds there. So we used up 6 electrons, meaning we now have 18 electrons left. Now, the next step step 3 is to assign these electrons to outside atoms to complete their octet, so our fluorine atoms. Each of these fluorines only has one bonding pair of electrons available to it, so they each need 3 lone pairs or 6 electrons. And it just so happens that if we do that 3 times, so 3 times 6 is 18, that will completely use up all of our remaining electrons. So we won't have any electrons to place down in step 4 of this process. So after step 3 and step 4, we end up with the structure you see there. A boron in the middle, 3 single bonds to fluorines, each of which has 3 lone pairs of electrons around it. Now here's where things are a little bit unique with boron. So with a normal molecule, what you would do is you check on the center atom, which is boron, and you count up the number of electrons around that, and you try to determine if we need to form any double or triple bonds to complete its octet. And if we look at boron right now, it's got 3 single bonds around it. So that should be 6 total electrons. And as the name octet rule implies, most atoms should want to have 8 electrons around them. Now, boron is an exception to this because it actually starts off with so few valence electrons, just 3 of them, that if this was maybe some other compound that didn't have boron in the middle, you might think we need to take a lone pair from one of our fluorines, let's say the one in the upper right there, and turn it into a double bond like this. So we'd have 2 lone pairs left there, and then two single bonded fluorines with 3 lone pairs each. So that is what you would do for a lot of compounds, but if you have 6 electrons around boron, that's actually okay. So in particular, with this example, this is not the right answer. And to go over why exactly that isn't the right answer, we can assign formal charges to these, and we'll go over the details of how to calculate that in a minute when we look at a problem with some resonance forms. But suffice to say, right now, I'm just going to show you the values. This boron has a formal charge of -1. 2 of our fluorines have a formal charge of 0. That part's okay. 0, 0. And this fluorine right here actually has a formal charge of +1. Now, one of the things about formal charges is you don't want positive formal charges to end up on electronegative atoms. So fluorine having a positive formal charge is really a big no-no, especially when our boron here has a -1 formal charge. So even though this gives us an octet, this is not going to be the right answer for this molecule. And this thing, which actually doesn't have a full octet around boron, is going to be the right answer. And really, again, this is something that only applies to boron. Most other atoms aren't okay with having 6 electrons around them. Okay, so for our next example, let's look at drawing the structure of phosphoric acid. And I'll give you a minute to try this on your own. So go ahead and pause the video. I'll come back in a couple of seconds and we'll go over what the right answer should be here. Okay, so hopefully you've tried this example on your own. We have 3 hydrogens, so we're going to have 1 valence electron from each of the 3 hydrogens. We have 1 phosphorus, and phosphorus has 5 valence electrons. It's directly beneath nitrogen. And then we have 4 oxygens. So 4 times 6, each of those oxygens. And so if we add all that together, we get 3 plus 5 is 8, plus 24 is going to be 32 electrons. So with that in hand, let's go ahead and start putting this molecule together. So in terms of the central atom, the best answer here is phosphorus. Now, it's never going to be hydrogen, so we can eliminate that possibility pretty much right away. So between phosphorus and oxygen, phosphorus tends to form more bonds than oxygen. It's directly beneath nitrogen, so it tends to form at least 3 bonds, and actually there's many examples, because it's in row 3, of it forming more than just 3 bonds. Oxygen normally only forms 2. And in addition to that, phosphorus is both to the left and below oxygen in the periodic table, so it's less electronegative. So all lines of evidence say we should probably have this phosphorus in the middle and attach our oxygens to the outside. Now you may notice that I put all 4 oxygens around the phosphorus and none of the hydrogens. And this is because hydrogen is really kind of a dead end in terms of a molecule, since it can only have one single bond. So we have 4 oxygens around our phosphorus, and we can start attaching hydrogens. Now, the hydrogens, of course, are going to go on our oxygen here. Now, the first hydrogen you can just assign to any one of these 4 oxygens equally well. Where does the next hydrogen go? And to help you figure this out, it's helpful to remember that oxygen should normally form 2 bonds and have 2 lone pairs. So specifically, oxygen doesn't usually have 3 bonds around it, usually just 2. And notice that when we put our oxygen, attached it to a hydrogen as well as the phosphorus that it was initially attached to, that already has 2 bonds. So we probably want to attach these hydrogens to 3 separate oxygens rather than attach them to the same oxygen, or like have one oxygen with 1 hydrogen and another with 2, for instance. Each of those 3 hydrogens should be attached to an oxygen, and just like the example from a couple of slides ago, you can attach those hydrogens to any one of the oxygens. So for instance, you could have attached one of the hydrogens to the top oxygen instead of one of the other positions. That's totally fine. So this is actually the skeleton of our molecule, and we actually put in a fair number of single bonds doing this. So the phosphorus, we have 4 phosphorus-oxygen single bonds, and then 3 oxygen-hydrogen single bonds, so that's 4 and 3 is 7 total bonds. So 14 electrons got used up, because each of those is a pair. So that means we have 32 minus 14, which is going to be 18 electrons remaining at this stage. So the next step is to complete the octet of our outside atoms. The hydrogens, of course, should just have 1 single bond and nothing else, but our oxygens currently only have 1 or 2 bonds around each of them. So what we need to do is assign these 18 electrons to our oxygens. So remember, we're completing their octets. We're not necessarily always assigning 3 electrons to each. So for instance, this oxygen on the left doesn't have 1 bond associated with it, it has 2. So we only need to put 2 lone pairs of electrons there. So we used up 4 there. We're going to use 4 on this bottom oxygen, and 4 more on this right oxygen. So let's see, that's 4 and 4 is 8, plus 4 more is 12. We have 6 more electrons left, and that happens to be the exact amount we need to complete the octet of this top oxygen there. So that's going to have 3 lone pairs. And so that uses up all of our electrons. We don't have any left. So in step 4, there's nothing to assign to the central phosphorus atom. Now step 5 asks us to examine the central atom, which again is phosphorus, determine if we have a complete octet. And it turns out that we do have a complete octet. This phosphorus is surrounded by 4 oxygens. There's 4 single bonds there, so that's 8 electrons around this guy. So there's nothing to do here in terms of forming any double or triple bonds. So this is your final structure for phosphoric acid. And again, the only difference here is which of the oxygens has 3 lone pairs and no hydrogens versus 2 lone pairs and 1 hydrogen. And you can put those at any three positions you want to. It doesn't have to look exactly the way that I have it there. All right.